Hello, everyone. This is Professor Ma, and this is the sections on determinant. Okay. The basic association with determinants is a calculations. It's a number first of all. Determinant of a square matrix is a number. In the 2x2 case, it's very simply is the diagonal product subtract the opposite diagonal product. Okay, and it associated with geometry. If I were to view AB as a point in two-dimensional plane and CD another point, and then what I get, this number actually is the area. So it's a sine. It's an area of the parallelogram. And this actually carry on to three-dimensional space. And if I take the three-dimensional determinants, it has this long formula which is not to be memorized. But the number we calculate is going to be the quote-unquote volume, yeah, with a sign. Again, okay. So let's start out with determinants. The determinants, we define determinants for n by n matrix, those square matrices. Okay. So for a 1 by 1 matrix, it just itself determinant of the matrix minus 3. 1 matrix, 1 by 1 is minus 3. And 2 by 2, it's the, as we said, it's the diagonal difference in that order. Okay. And again, we have motivations of these when we put the coordinates, the row as coordinates of points, and then these numbers, we're going to get the area with a sign. Okay, and why is that? Well, first let's demonstrate that is the case for this simpler case where one of the point and it sits on x-axis. Okay. And then if we put this into a matrix A0 and the second point CD in that manners, and I take the determinants, and this is of course A times D, right? And notice A is from here to here, and D is from here to here, the height. So yes, and therefore you get the area of the parallelogram. When we switch, it says, whatever we switch the orders, if I place them in the matrix, if I put the point AB over here on the pictures, A0 down below, then I will get determinant of this. I will get 0 minus A times D, so I will get a negative AD. Okay, just because I switch these two rows. So what's the meaning of that? Well, that minus sign actually tell us the relative positions of the 2 points, AB and A0 and CD. So here is what a minus sign means. Okay, suppose we have the first point A is situated at AB, okay, and not 0, 0. And then we have another point B, the second row of the matrix, CD, somewhere on the plane. Then there are two possibilities. That B is either on the left-hand side or on the right-hand side of the point A. Now, what I meant by that is this. If I need to turn this red arrow based on A to point at the point B in the left-hand side, I need to turn left. Okay, if that's the case, then the determinant is going to be positive when I do put A, B, C, D in 2 by 2. Okay, if I put A on top, B on the bottom. If on the other hand, if the point B, I need to make the red arrow point at point B, I need to make it's on the right-hand side. And then the determinant is going to be negative. Okay? So that's what I meant by the relative positions of the point A and B. So in other words, it coincides with, well, in these situations, in the first situation, if I interpret this to be X, and this is Y, and then then basically this is a rotation of the XY coordinate, our usual XY coordinate. I can rotate it, make it look exactly like that one. So it's the same orientations as our XY. This is our X coordinate, 1, 0, and 0, 1 is Y, that way. So these orientations is the same as these situations. Okay. As opposed the other way, if we switch the X and Y label around, we put the Y on top, then the orientations, the relationship of these two rows, who's on the right, who's on the left, switched. Okay. That's what the plus and minus sign is. Okay. It's the orders of the two axes. So in these situations, here's X, Y. And if I rotate it, I can make it look like X. It fits these orientations by rotating the blue one, it fits the green one. So they are the same orientation. Therefore, the determinants of A, B first, C, D second will be positive. Whereupon, if I write down the determinant of C, D, A, B, there will be a negative number for the area. So area of this parallelogram is just determinant of 5 minus 3. And then CD, the second point to the left, is 1, 4. And this will guarantee it's positive. Okay. Well, one of the motivations for usage for 2x2 determinants is there's a formula for solving system equations for 2x2 equation using that. Okay. And it's called the oh, excuse me. It's called a Cramer's rule. Okay. So the premise of Cramer's rule is, first of all, you need a system where these coefficients, we put in the matrix, the determinant of this is not 0. Okay. The reason is because the formula involves dividing by this number the determinants. So here's Cramer's rule. It says, in this case, first of all, the determinants of the coefficient is matrix 1, 1, 1, 4 is 3. Okay, 4 minus 1 is 3. And so how do we get the formula for X? Here's the formula for X. You replace the number in the X, the 1, 1, by the numbers sits over the constant terms on the other side. Okay, so, and take determinant of that and divide by the determinant of the coefficients. And so this is just a mechanics. It works out, and you can kind of, if you can almost look at the formulas and getting answers, things like that. So that similarly for Y, you do the same thing, except you put the 2, 5, the constant terms put over here in the second position, over here, okay, for the Y columns. Okay. And so this is Cramer's rule. It's yeah, it's okay. It's not used much. It's interesting. In general, there's a determinant can be generalized to 3 by 3. Okay, and we do something called by determined by the first row. Okay, so how do you do that? We start out with the first entry of the first row and extract the entry A and then multiply that times the determinant of the matrix that's left over, the corner matrix over here, a submatrix. Okay, then we subtract, then we go on to, like over here, 1 times this matrix left over here. Okay, the second step, then go on to the second entries. Remember, we're doing this across the first row. So we're going to the second entries and put that down. And notice now we're going to switch the sign to a subtraction. Okay, you just have to memorize these flip-flop signs. And then multiply by the determinants of crossing where the second entry situated, the row and the column is set up. So in this case, it's going to be 0 minus 0 times. Well, we can stop there because I really don't care what the determinant of this is, but it's going to be 0. Okay. Then the third terms is going to be extract the numbers here. And again, the signs now switch back to that and we multiply C, the entry, times the determinants of the submatrix to the left corners. Okay. And then we can calculate the 2 by 2 determinants and then finally collect the arithmetics. Okay. So get determinant of this is 7. This method of doing that we say is expansion by the first row, because we use the first row A, B, C to do these, to put into a 2 by 2 determinant, expand it into 2 by 2. Okay, and then this so-called butterfly methods. Okay, and with butterfly method, it's you copy the first 2 rows over here. I'm sorry, first 2 columns, and copy on the other side, make it bigger. Then we're going to multiply all the diagonals from top left to the lower right, the 3 of them, and add them together. And then we're going to subtract all the opposite diagonal product. Okay. And so it's 4 and 0, 0. So we're going to wind up with the same answer, minus 1 plus 12 minus 4. Okay. The determinant of 3 by 3 matrix is the volume, the sign volume of this, the official name of this object is called parallel pipe. Okay. I won't try to spell it. We'll just say it's a box, that's a squashed box. Okay. Again, for any solid, and basically you get a plus or minus sign depending on if I switch 2 of the rows to two positions. If I switch 2 of them, then I change the sign of the determinants. Okay, so get a plus and a minus. And the plus means that the coordinate system we have, the solid basically is the same way as our XYZ 3-dimensional coordinate system. Or in other words, think of this: if I plot something XYZ 3-dimensional coordinates, now I plot the same except with the X and Y coordinates swapped. Okay, that the image is going to be a left-hand copy of the first one. If the first one is a right-hand copy, we say, then the other one will be a mirror image of that copy. And those basically is why there's a plus and a minus sign in these 2 copy of orientations. Okay. These are 3 by 3 Kramer's rules, and you can find out how to do that, but we will not going to talk about that. So usually used to be in textbooks, but too many steps. Okay, so if you need it for some purpose, you can find it out on the internet easily. It's very similar to the 2x2. Okay, it's just too many steps to do it. Actually, practice using it. Determinants 2x2 is area, 3x3 is volume, so we can use that to generalize what we mean by n volume of an n-dimensional solid using determinants in a sense. So here is the general matrix expansions of n by n determinants by first row. So here we go. It's just like the 3x3 one. We take the first, okay. First, let's talk about what we mean by the submatrix A23. Okay, submatrix A23 means you look at the matrix, the two suites about these entries, this position here, and A23 means you cross them out. Okay, whatever left, okay, is a small matrix. That's what we mean by A23 here. Okay, so Aij on the left hand side, it means cross out the ith row j's column. Okay, and so here's how the first row expansion works. Okay, you take the first entry, okay, multiply by the determinant of this A11. What's that again? Cross that out, cross these out, and what's left over, that's the A11. Okay. And that's a smaller square matrix. You need to calculate the determinant of that. Okay. And that, of course, if it's not 2x2, if the 3x3, you have to break it down further. So you can imagine this is quite a problem of like peeling your onions. Each layer is, we have to keep doing it. And then we go on to the next terms, which is that you cross that out, and that of course left over here and here. That's the A12. You take A12, that capital A12. Then you take the entry A12 multiply by the determinant of that, and that's a number. And then you go down the row until you exhaust all the entries in the row. Okay. So using these formulas, that's where we get the 3x3 expansions. Okay. And here's a 4x4 expansions. I'm going to do it across the first row. Okay. 2 times what's left over, the determinant of what's the smaller one. Okay. Plus minus 0, plus minus sign swap. Okay. Of the determinants of all the stuff left over here, but since it's 0, it's going to be 0. So that plus minus 1 times determinants of the green part, okay, the minus, and then finally the last entry 0 times the determinants of this green part, which is 0. Okay, so you get 0 again, and then we do a 3x3 expansions of the other two, and you get minus 11. So that's it. That's how we do a row expansion of bigger matrices, bigger size matrices. Okay, and then you can easily find out on the internet, Google, so you can test this similar expansion method. You can do according to any column or any row for calculating determinants. Okay, and we will stop here. Okay, that's it. Bye-bye.